All right, so we have already introduced data preprocessing, and we discussed how high quality data is very important in data preprocessing. If you recall, we said high quality data leads to accurate models, and accurate models leads to accurate prediction. So in this video, I want us to now look at one of the major steps or major components of data preprocessing. Okay. And that's data cleaning. Okay. So let's go to the next slide here. We know that data in the real world is dirty, it's messy, incomplete, noisy, and inconsistent. Okay. So let's look at an example in each of these. So when we talk about incomplete data, okay, so oftentimes we'll end up having missing values. Missing values, in this case, we have double quotation mark, means that we don't have a value for this. Could be asking a candidate, what's your occupation, and then for some reason our database doesn't have that value. That's an incomplete data. Okay. Noisy data means a good example is this: a -10. We know that you can't have a -10 salary. Okay. Again, when you talk about inconsistent data, you can see here, your date of birth says you're born in 2010, right? However, you indicate that your age is actually 42. These are some of the things that we are saying here, that this happens in the real world. That is inconsistent data. Okay. But really here, we need to ask ourselves, what is noise, right? So by definition, we can say noise is just a random error or variance. In fact, this is just random variance. Okay. Random variance. Okay. That's actually measured in a variable, in a measured variable. Okay. So what are some of the, and this, there could be many reasons for this, right? But the most important thing here we want to review here is how do we handle this messy, dirty data. Okay. So now let's go ahead and look at some of the ways to handle some of these anomalies. Okay. So the first strategy is to ignore the tuple. Okay. Now we use this strategy to, especially when we have a missing label, class label. Class label here, we'll see probably is just a Y. Okay. And this Y is just nothing but your dependent variable, right? So you could have X1 here for your attribute. We have X2, and remember, this can just be columns in a table, right? If you have a table like this, okay, so all these columns would be X1, maybe X1, X2, and so on and so forth. And then your Y here, we call this the class label, right? So you might decide, okay, we're gonna ignore this record that has a missing label and only retain those that have a class label. Okay. Well, so what's the problem here? This might look very simple, but might not be very effective, right? Unless really you have so many of these tuples containing several attributes with missing values. All right. And the reason for this is, it's very poor when the percentage of missing attributes varies considerably. So this is not the best approach, really. Okay. Another strategy here is to fill in the missing values manually, right? Okay. Well, what if you have 1 million tuples or records, right? So this approach will be untenable, time-consuming, right? It's not feasible, all right, given that you have a very large data set with missing values. Okay. Another strategy is to fill automatically data with a constant, right? Meaning you just replace the missing value with a constant. This constant would be maybe an unknown, could say unknown, right? Okay, so just say this is unknown, all right? But in R or Python, sometimes we use this, could just say none or NA, right? So again, here we just say unknown, all right? we just give it a label, or in some cases, we just put a -1. So our compiler will just know that actually that's a missing value. Okay. Well, use this sparingly because sometimes some of our mining program might mistakenly think that, you know, it's an interesting concept. So again, this is not foolproof. All right. So let's look at another example. So another strategy which might be important here is to use a measure of central tendency, right, for the attribute. And what I mean here, we could use mean, right? So we have mean here, okay? And we could use median, all right? So we have median here. These are just measures of central tendency, right? Okay. One thing I just need to bring to your attention here, when you're going to be using mean, then make sure your distribution is normal. You know, it follows a Gaussian distribution. Okay, very important. In this case, you can use the mean. So when do you use a median? When your data is skewed. So for example, here we have maybe a positively skewed data, right? Or sometimes you can have data that is actually skewed to the right like that. So in this case, you might need to use median. Median will be the best measure of central tendency to use here. Okay. And an example here. So you could have, you could replace the attribute mean with an average salary for that training example, or you know, you use the attribute mean for the same class, right? You could use that for the column, or you could just get the mean for all the different tuples and get the, you know, the average for that. And then for every missing value, you replace that with the mean. So these are just two approaches you can actually use for the mean. Okay. Again, just to emphasize, so if you had this class level, let's say it's Y, right? And this is just different salaries for, let's say, different flow managers, right? So make sure this is just the same class level for flow managers. Don't mix it up with other salary for other employees, right? So you collect all these salaries, let's say for, you know, we had 100 flow managers, and you know, we had missing values, right? And we could only get maybe 80 of this, right? So you get the average of all this 80, and then for all these missing values for 20, you replace that with the average salary for this. Okay, so let's say the average salary here was maybe 5K. All right, so for every missing value here, you replace it with 5K. Okay, so that's what we mean by replacing that with the attribute mean for this attribute here. So this attribute here, maybe we call this salary, right? This attribute is called salary. Okay. All right. And then the most probable approach is actually to use, let's see. So the other best approach is maybe to determine that by using regression, okay, or maybe Bayesian. Okay, and when using linear regression, I'll show you in a few slides. You just try to fit a best line of fit, right? And then you try to use that to predict, you know, variables that are close to one another, right? Another approach here, when you're actually doing some estimation, you could use inference-based tools like Bayesian, formalism, or decision trees. Okay, so you can actually use decision trees here. You can actually draw a decision tree, is hierarchical in nature, and then, you know, actually create a decision tree, right, to predict the missing value for maybe, in our case here, salary or income. Okay. Well, so in summary here, we could say, you know, this 1, 2, 3 kind of just bias the data, right? When you know, especially when you fill the value and those values are not correct, then what? Okay. So the most popular strategy here is to probably use linear regression, Bayesian formalism, right? Or, you know, just construct a decision tree to sort of predict the missing values, right? So one of the questions here will be, why should we do this? Why is it a popular strategy, right? So we are saying here, by considering these attributes that are close to one another, right, there's a great chance that the relationship between the salary or income with other attributes will be preserved, right? That relationship will be preserved and will just reflect a more accurate data, okay? Again, one thing to note here is a missing value may not just imply an error in the data, okay? What this means is, just consider another example here, right? Let's say you're applying for a credit card, right? And maybe this candidate, or maybe candidates, may be asked to give out their driver's license number. What if you don't have a license number, right? So it's just natural that you leave that space blank. So during design of some of the system, it's important that you provide those provisions so that in the form, the respondents can specify values like not applicable. So very important. Okay. All right. So let's continue here. So the other thing I wanted to mention here is, so how do we, take care of noisy data, right? So given a numeric attribute, let's say price. In our case here, we have a price of a product, right? How do we smooth the data to remove the noise? Okay. So in this case, we have some random numbers, right? Let's say we have 4, right? So actually here we have 4. Let's say 15. We have 34, right? We have 28. Okay. 25. All right. Then we have 21. We have 8. And we have maybe another 21. Okay. Okay. So first of all, let's look at the first approach, right? Binning, right? So binning essentially is just trying to partition this data into bins, right? Okay. Or what we call buckets, right? We call this buckets. Okay. So this is a very popular strategy for smoothing. What that means, first of all, the first thing, you need to sort this data in ascending order. So you start with the smallest all the way to the largest. So first of all, the first step is to sort out this data. Okay. Now there's something called equal frequency bin. So in this case, you wanna first of all sort this into ascending order, sort the data. Okay. All right. Then once you do that, you partition this data into buckets or bins. We call this local smoothing. Okay. All right. We call that local smoothing. So again, in this example, now the data for our price here are first sorted and then partitioned into equal frequency. So our bin size here equals to 3, for example, as you can see here. All right. So once we have that, then we can now, ensure that for each bin, we have an equal number of elements, right, that can fit there. And again, we've already managed to smooth by equal frequency, right? Another approach is to use bin by means, right? So this is just, we kind of leverage on what we've already done here. So we take the mean of this bucket. So 4 plus 8 plus 15 divided by 3, we get 9, right? And then we just come and replace for every value that was here, 4, we replace with the mean for this. So the mean here is 9. So we just come and replace all this with 9, 9, 9. And we do that for bin 2 and bin 3. Okay. Another approach here is bin by boundaries, right? First of all, we establish the minimum, okay, and the maximum. Okay. So essentially here, the minimum for bin 1 is 4 and the maximum is 15. So we come and check here. So is this 4 closer to, so let's say here, minimum is 4 and maximum is 15, right? And then we just cross check. So 4, is it closer to 4 or 15? If it's closer to 4, then we replace that with 4, right? It's just by the borderline. right, of the minimum. Then we check for 8. Okay, what's the distance from 4 and the distance from 15, right? If we check that closely, we'll see it's closer to 14. And 15 is just right on the maximum bound. Repeat the same procedure for all this. As you can see here, this is just on the boundary. 28 apparently is closer to 25. So that's why it becomes 25. And that's it. And that's binning. So we've completed here binning, right? So now let's look at, so in general here, another thing I just want to mention here. So in general, the larger the width, the greater the effect of smoothing. I mean, the more data you have, then you'll have a better smoothing mechanism, right? And we're saying here, another alternative is that bins may be of equal. Sometimes you'll find in literature or during your reading, you have something called equal width, right? So binning by equal width. Okay. So let me just put that one. Okay. So here we're saying you establish the intervals between the range of values in each bin must be constant. All right. And again, we're saying here, binning also be a very good approach to use for discretization technique. We'll look at that later. All right. So let's move on. Another approach is to use regression. So there are two types of regression here. And the first one, the most common type is linear regression, right? Linear regression just involves is the process of finding the best line. As you can see, the best line that can fit two attributes, in our case here, or two variables, right? We have quarterly change in GDP, first attribute here, and unemployment rate, right? Okay, so that one attribute can be used to predict the other, right? What if we have more than one attribute or more than two attributes, right? In this case, we now use what we call multiple linear regression. Okay, if you've taken a statistics class, you'll come across that multiple linear regression. Okay, which is just an extension of the linear regression. Okay, where we have more than two attributes that are involved, right? And the data are kind of projected into a multidimensional surface because we have more than two attributes. We cannot represent that on a 2D plot. Okay, and then lastly here, the last strategy here of handling noise is something called clustering. Okay, so clustering here, we can also call it outlier analysis. So I'll just say outlier here, outlier analysis, right? Analysis, I'll abbreviate that. Okay, or you can also call this cluster analysis, right? So cluster analysis. So in literature, you'll find that we use these terms interchangeably. Okay. Now, so by definition here, what is an outlier? Okay, so outlier just values that are far away from any cluster, right? So clustering analysis here, what we are doing here is we're just trying to group similar values. Okay, we're trying to group similar values, okay, into groups, clusters. So we can say this is our first cluster, all right? Cluster 1, cluster 2, and cluster 3. Okay, and then these values that don't fit in any of these clusters are now considered as outliers, right? So once you identify these are outliers, you can go ahead and start, you can make a decision how to treat them. Do you want to remove them from your data set? Okay, in fact, incidentally, this is just a 2D plot that shows the customer locations in a city, in 3 data clusters. Okay, so clustering might be very useful to reveal some of these anomalies, right, or outliers in our case here. And like I said, our outliers are just values that are far away from a cluster or a grouping. Okay, and that's it. So what's the story so far? So we can say here in conclusion that many data smoothing techniques can be used for data discretization, which is just another form of data transformation, right? And data reduction. In fact, we already looked at binning. Okay, so binning here might be considered as a form of data reduction. Okay, because we were able to, in fact, if you go back here, you'll see we would try to reduce all these different values, right, into distinct values, right? let's go here into distinct values, right? We wanted to reduce the number of distinct values per attribute. Okay, that's a form of data reduction. Okay, so all in all, we've already determined that missing values, noise, and inconsistencies contribute to inaccurate data. Okay, it's not good. So you need to actually perform some data cleaning. All right. And again, here, so far, we've looked at different techniques for handling noise, missing data, and smoothing data. You should be very familiar with that, because, you know, when you're dealing with big data, right, you can now understand how data cleaning might be a big challenge. Okay. And that's it. So in our next video, we're going to look at data integration, right, as our next major component, data preprocessing. All right, thank you.